Hello! Due to the state of the world currently, there of course will not be live performances for this year's Midlothian Science Festival, unfortunately. So for this week's video, we are going to be going back to a video we recorded at the Midlothian Science Festival Blast from the Past Victorian Science Gala at the National Mining Museum, Scotland, back in October of 2018. Let's get on with the show. Right, good afternoon and welcome to the Science of Candles and why they're amazing. Now, we are going to be talking, of course, about candles. But we're going to discuss candles, we're going to talk about a man called Michael Faraday. Now, Michael Faraday was one of the true trailblazers of science communication. He was best known for his talks at the Royal Institute's Christmas lectures. And people used to flock from far and wide to see what amazing things he'd bring. Be it a Faraday cage or be it standing in the middle of lightning. But then, one year, he surprised everyone when Michael Faraday walked in and put on the table a single candle. And Michael Faraday went on to talk about that candle for 6 one-hour lectures. The lectures called The Chemical History of the Candle. Now, this really shows us exactly how a candle works. Now, Michael Faraday described plain candles as having what he called beauty in utility. He said that they were beautiful because they did exactly what they're supposed to do. A candle burns with a steady flame. It's nice and safe. And the way it does that is it's got a little cup formed inside of it as it melts. That cup is full of melted wax. That wax then gets turned into a gas. It evaporates. And that wax vapour acts as the fuel for our fire. As the fire goes too low, the wax puts it out from the bottom. It allows it to burn from further up. But to really explain why that forms, well, we are going to take a bit of a trip back in time. Back to the appropriately October, spooky-themed Victorian era. Now, one of Michael Faraday's colleagues actually described how you can see the way that a flame acts by looking at its shadow. Now, Michael Faraday himself never actually did this. His colleague described it quite well using this technique, but we're actually going to look at it today and see how heat rises. So if we're going to light there, and then place a flame in front of it, we will see the shadow of a flame. And with that you see how the hot air rising forms the shape of fire. It goes up and around. That's why it's a rounded bottom on a flame and going towards a point. It's that air pushing it up.
That's amazing.
But it's quite strange that I said that fuel for a candle is wax. Because wax usually just melts when you heat it up, doesn't it? It doesn't usually burst into flames. That's what we think of wax as doing. If I hold this bit of wax in front of a flame, it's not on fire, is it? No, it's dripping. Well, it is, like I said, the wax vapour that is actually acting as the fuel. And we can show this quite easily. Because whenever you blow out a candle, there's smoke. That smoke is wax vapour. So if I take a flame here, I'm going to put out our candle, and then pop this flame into that vapour. And our flame will travel along the vapour, hopefully. And back down to the wick. What we have to do is snuff it out. Come on. And it'll travel back down. Now, we can further prove that it is in fact the wax vapour doing this, and that the wax is the fuel. Now, what we're going to do is we're going to take a burnt out match, one where the fuel has been used from the wood, and that will no longer ignite. It will glow as it heats, it won't light on fire. But if we dip this into some melted wax and coat it in a fresh source of fuel, then pop this same match back into our flame, it is a larger flame than was ever given by the match itself. So right there you can really see the combustibility of wax. But fuel is not the only thing that you need for a flame. Another thing that you need is oxygen. And the easiest way to prove that we need oxygen is simply to restrict the amount of oxygen that gets to a flame. If I put this glass on top of here, that flame will burn through the available oxygen in the air. And eventually, that flame will start to dwindle. And it will go out. We entirely need that oxygen-rich environment in order to have fire. And we can show this chemically as well. If I take another candle, say the one I've got in here. Now, this one is surrounded by this white powder. That is bicarbonate of soda. I'm going to light up this candle, and then I'm going to put on some acetic acid solution, better known as vinegar. So, I take our vinegar and squirt it onto our bicarbonate of soda. This causes a chemical reaction which releases carbon dioxide gas. Now, carbon dioxide is often used in fire extinguishers, and this is why. Carbon dioxide is denser than the air around us. Because of that, it fills up that beaker, pushes the air with oxygen upwards. It displaces it, meaning that no oxygen can get to the wick where the flame was, and it puts our flame out. But that leaves the question of what exactly would happen if we were to do the opposite, if we were to increase the amount of available oxygen. Well, this is also something that we can do with a chemical, I don't want to say reaction, with a chemical catalyzation. So, I've got some hydrogen peroxide here, H2O2. It's very nasty stuff, as illustrated by the old joke, two chemists walk into a bar. One of them says, I'll have a glass of H2O. The other one says, I'll have a glass of H2O2. The second one dies. Now, that is the formula for hydrogen peroxide. It's H2O2. It's a lot like water, but with extra oxygen. And left open, it will actually degrade. It will decompose into oxygen and water. Well, that takes a long time. So we're going to speed that up using this black powder inside of here. That is manganese dioxide. And that will act as a catalyst for our hydrogen peroxide to decompose. So when I pour this into here, you will see it bubble. And that bubbling is oxygen. We've got oxygen bubbles in there now. And if I take a flame and then blow it out, because we don't need a flame, just have an ember, a little bit of heat, pop it into our oxygen. We get a flame returning. Because normally our atmosphere is only about 21% oxygen, not enough for this ember. Inside this test tube it is now about 80%. More than enough for this to burst back into flames with a little pop. There's actually a small explosion. If I put this flame into our oxygen, you actually see it get brighter as it's using up more of that oxygen. Now, we're used to oxygen in the air around us, Mike. We see that every day. And, well, we just saw it as a liquid. But very rarely do you get to see oxygen locked away inside of a solid. Inside of a solid compound. Well, this shiny black powder here is potassium permanganate. Potassium permanganate is KMnO4. There is a lot of oxygen in potassium permanganate. And this one is going to require a blast shield. And this one is the reason that the fire alarm went off earlier. Okay, so what we're going to do for this is we are going to squeeze on a little bit of glycerin. Now, glycerin is a sugar syrup. It is very good for sore throats. You can get it at most chemists. It's also absolutely beautiful for icing. I highly recommend it if you are an avid baker. But when we put it onto potassium permanganate, which is very, very high in sugar, it actually reacts with it. So we pour some onto here, and then get well out of the way. That will actually start to react, and this reaction is exothermic. It actually releases a lot of heat, which means we've got heat, we've got a lot of oxygen, and we've also got a fuel in the form of our glycerin. These three things together will inevitably lead to spontaneous combustion on any minute now.
Oh my goodness! That's amazing!
Now you may have noticed the colour of that flame. When it burst up, it was purple. Now the reason it was purple was because of the potassium in our potassium permanganate. Now potassium is a metal, and that's exactly how you make fireworks, get the beautiful colours is using different metals. Potassium happens to give off a flame signature of a sort of lilac-y shade, which is why we had that beautiful purple in that reaction. Now, I did put a fair bit of sugar in that one, so I'm going to let it burn down for a little bit. Oh, it's like burning a marshmallow. Oh, you can almost smell the sugar. You can't, it smells awful. But, right there, that is exactly why having those three things together can be so dangerous. Let's see if we can use our old trick. Let's see if we can just start it with some oxygen. There we go. So, now we're going to come to the conclusion of this, how we can manipulate fire. Because one of the greatest achievements of humanity, and the greatest achievement certainly of the Industrial Revolution, the Victorian era, was fully harnessing fire. It gave us things like steam engines, all those brilliant ideas, and most inventions since then have been due in some part to the harnessing of fire. Well, I've built a little contraption of my own here. This used to hold pencils. This is mostly wood. Underneath, we've got a fad from last year, a fidget spinner. Now, what I'm going to do is I'm going to put some methylated spirit into this. Methylated spirit is a kind of alcohol. It is very flammable, and it's going to mix together with boric acid, which I've put into the bottom. Boric acid happens to burn with a beautiful green colour. So I'm going to pop that in there. So now we're going to have a lovely green flame. But the reason it spins is so we can manipulate the airflow. We need that oxygen. The flame will follow the flow of oxygen, which means when that's spinning and we force air around it, we won't just have a green flame, we'll have a green fire tornado.
Oh my goodness.
And that shows the level that we are now able to manipulate fire. Something that was previously feared, we can now turn into a coloured, twisting, dancing feature to finish off a Victorian era themed Halloween show. And with that does bring us to the end. So thank you all very much and enjoy the rest of the gala. Thank you. Oh, that's smoky. Don't worry, that smoke is mostly water, it's fine to breathe in. It's water and a little bit of carbon dioxide actually, so fire landing on the floor would probably go out right now. And that does bring us to the end. Thank you very much for watching. Please do share, like and subscribe. And next week we'll be taking a bit of a closer look at some of the science from that show that was a bit difficult to see from that distance. But until then, please do carry on learning. I'll see you next time. Bye.